Good morning, everyone. Welcome to One Concept Per Day portal. And today's concept is about binding energy, understanding about the concept on nuclear energy or binding energy per nucleon graph, and then also looking at how activity can also be estimated using this. So, and many more questions on this. Okay, especially focus only on binding energy. Okay, so this question is taken from November 2005 paper, which is TZ0 second paper. Right. Now let us begin with this. So the start state, what is meant by a nucleon? What's a nucleon? A nucleon can be either a proton or a neutron. Since there's a one mark, you can just say it's a part of a nucleus. You can say it is either a proton or a neutron. It's a constituent of a nucleus. Second question, define what is meant by the binding energy of a nucleus. What's meant by binding energy? It is the amount of energy required to break a nucleus completely into its constituents. How do you want to break it across? So how much amount of energy you need to supply so that you can break a nucleus into completely into its constituents, you can say. So this is meant by binding energy of a nucleus. Okay, now let us move on to the next one. The graph shows below the variation with nucleon number of the binding energy per nucleon. Okay, so it's a graph which shows about the nucleon number, which is a mass number, versus binding energy per nucleon. This is a very famous graph. Many people would have studied this. Many places you have learned this. But let us understand how do you solve this one here. Now, what is the question over here? So you can see, I can just interpret the graph here. It says it's helium over here. I think this should be 3H, and this is a lithium, this is beryllium, oxygen 16, 56 ferrous, 138 barium, 208 lumbaco, 235 uranium. Now what you observe here is that this is not the binding energy, it is a binding energy per unit nucleon. Per nucleon is what has been given over here, first thing. And then you see the binding energy per nucleon keeps on increasing with the increasing mass numbers very rapidly. And after some time, when it reaches the ferrous, when you see in between oxygen and ferrous, it shows a nonlinear behavior. And after ferrous to uranium, it shows something like a declining curve. Okay. Now let us read the question what has been asked. Use the graph to explain why the energy can be released in both fission and fusion process. Now if you see here, ferrous makes the peak. So the value of the binding energy per unit nucleon for ferrous could be somewhere around 8.7 million electron volt. Okay, per nucleon is nothing but so much over here. Binding energy is given over here per unit. Now if I draw a line here, I'll draw a line here. This is at 56 over here. So if I want to create elements starting from hydrogen to iron, I can go in this direction by the method of fusion. What is fusion? Fusion is nothing but the number of nuclei. You take several nuclei joined together, smaller nuclei joined together, you get a fusion. Then if you look at uranium to until the iron in this direction, then the elements formed here are formed using fission reaction. What do you mean by fission reaction? Fission reaction is nothing but you take a heavy nucleus, break them into smaller parts, and therefore these smaller parts could be something like these smaller nucleons. Okay, now what is being asked? He is asking you to find out why energy can be released both in fission and as well as in fusion process. Okay, now what we do is, let me assume some nuclei. Let us take for example, there's a nuclei like what shall we assume? Shall we take for example, we take beryllium for example. We take beryllium. Beryllium, what is the binding energy per nucleon for this? This is seen to be 6, this is 7, it's not 6.5, maybe 6.4. Let's take some approximate value, 6.4 over here. Beryllium is being formed with lithium. What is this lithium over here? Lithium 6 is something like 5.2, 5.3. I can take the value equal to 5.3 here. 5.3 here. And hydrogen 3, the H3 here. So what is this now? This is around 2.9. 2.9. I'll assume that 3 plus 6 gives rise to 9. Okay, simple. So when I do something like this, okay, this has been formed, and I need to prove whether energy is being released or energy is being absorbed. That's what we need to do. So towards it, now this during fusion, what's happening? So if it is energy released, delta E, I take energy of products minus energy of reactants. Okay, simple thing that you use in chemistry. So what is the energy of the product over here? So it says product, which is the product here? 9 beryllium is a product. So there are the binding energy per nucleon for this one is going to be 6.4. 6.4 per nucleon. These are 9 nucleons. I'll multiply this by 9 minus reactants. What are the reactants? Lithium and fusion. How many? What is the binding energy of this? 5.3 minus 5.3 multiplied by how many nucleons? 6 over here plus. Now this is 2.9. It's 2.9 multiplied by 2.9 multiplied by 3 and write like this. So which should now be, now if I take the calculator and find out what is the value I get 6.4 multiplied by 9 is equal to so much minus 5.3 into 6 is equal to so much minus 2.9 into 3 is equal to 17.1. 17.1. 17.1, what is it now? Is million electron volt here, right? So this should also be MeV over here. Which means, what does it tell you? That means this delta E is positive. It means definitely our assumption that there is amount of energy being released. Whenever delta E is positive, energy is released. So we have found out that in fusion, energy is released. Okay. Now let us redo the same thing in case of fission also. So in fission, I am just showing you an example over here. Okay. So delta E, for example, here if I take uranium-235. Uranium-235, what is this? This is a bigger nucleus I have, right? This is around the 7 point, I'll write down here. This is around the 7.4 MeV. Okay, for uranium. I'll write down here 7.4 MeV here. This has 235. Let me assume this has been broken down using 208 and one more nucleus. Okay, so 235 is equal to 208 plus how much is it? 15 minus 7, 8 is 7. Will it be much more? Okay, it will be much more lesser. I'll do one thing. I'll not take 208. I'll take 138 here. 138. Because fission happens in this region, right? I'll take upon the smaller nuclei. 138 plus, now what is 15 minus 8? 15 minus 8 would be 7 once again. And here it is 12 minus 3, which is 97. 97. So where is 97 corresponding to? I have a point 97 here by here. If I draw a line nearby to here, it could land somewhere over here. Okay. So corresponding value here could be, how much this will be? This will be around 8.5. This will be around 8.5 MeV. 8.5 MeV per A. Okay. Now let us use the same thing. What are the products over here? Products here is this 8.5 MeV is one of them. 8.5 multiplied by 97 nucleons plus, and what is the other product? 138 BA. 138 multiplied by, what is the value of this? 138 BA. What is it now? Somewhere we missed it here. Just a minute. This would be around 8.4 and 97 could be around 8.5. Okay, 134, 8.4. 8.4 into 138 minus, now uranium-235, how much is 7.4? So this should be 7.4 into 235. 235. Okay, let us calculate what is this value. If I get to be positive, this is the energy of products and this is the energy of reactants. Okay, so let me see whether you get positive or negative for this. So I get 8.5 into 97 plus 8.4 multiplied by 138 is equal to so much minus 7.4 into 235. I get 244.7. 244.7 MeV. Which means what? So in both the cases, okay, delta E is seen to be positive. Now how much do I write here? Now these are 3 marks. Okay, the first mark can be said that about if binding energy. Why does this happen? Binding energy per nucleon is seen to be increasing when A increases during fusion. I have just shown an example. Okay, if you have time, you can write this example. Otherwise, you can just show it like this over here. See, binding energy per nucleon increases for A as A increases for fusion until how much? Until ferrous. Okay, until 56 ferrous. Therefore, what will happen now? Therefore, I can say binding energy per nucleon into number of products or product minus reactant will be equal to binding energy per nucleon, okay, into product. What will be product? Let us say this will be A2 minus A1. A2 minus A1. Now binding energy per nucleon BE by A is positive. A2 minus A1 is also positive. Therefore, change in binding energy is positive, which means energy is released. This is what we can say. Now, let us look at the second one. So, this is, we have proved it for fusion. Now, binding energy per nucleon for fission starts increasing from where? From uranium 235 to Fe6, right? Fe56. So therefore, what happens? Delta binding energy is equal to energy released. Which should now be equal to what? Binding energy per nucleon multiplied by, once again, A2 minus A1. Now what is A2? A2, see, this is your binding energy curve. This is your binding energy curve. It comes like this also, right? This is your binding energy curve. So this would be your A1. This would be your A2, right? When it went like this was your A1 and this was your A2. Now it is going like this over here. So as a result of it, once again, A2 minus A1 is equal to positive, and therefore what will happen? So delta binding energy is equal to positive, and hence energy is released in both the products. I think it is clear now. Okay, so don't assume that, okay, when I when you bring in two nucleons and join them together, energy is released, energy is being brought in, and so on. Okay, so therefore, in both the cases, energy is being released. Okay, I proved mathematically and I also showed you logically. Let us look at the next one. Carbon 11 undergoes beta positive decay. What is beta positive decay? Positron decay. With a half-life of 20.5 minutes to form an isotope of boron. Write down the nuclear reaction for this decay. Write down the nuclear reaction. Very easy question. What we'll do is we'll write 6C11 gives rise to positrons, means what? It is +1 E0, positive electron. If I put +1 over here, then what should I get over here? I will get some X over here. If this is 6, this should be 5. So that 5 plus 1 becomes 6. And 11, and here you should have 11 over here. 11 over here. 11 plus 0 becomes 11. So, and then, now you see, whenever there is a positron decay over here, you should also get a neutrino over here. Okay? Because this is an antiparticle, so you should get a real particle over here. Okay? This is what you call as a neutrino hypothesis, which you have already learned. So this is how it works. Okay, next. Deduce that the sample of carbon 11 of mass 1 into 10 to the power minus 15 kg contains 5.5 into 10 to the power of 11 atoms. Okay, so you need to prove that a sample of carbon 11 mass, carbon 11 of so much mass contains this much. This much mass of carbon 11 contains this much number of atoms. So how do we do it? So always remember, whenever there is an element given, and if you know what is the mass number of it, then what you do is take the mass number. What is the mass number here? Nucleon number. How many nucleons are there? 11 nucleons. 11 nucleons of carbon will weigh Avogadro number of atoms. Will contain Avogadro number of atoms. So therefore, now what do we have here? 11 grams, not 11 nuclei, 11 grams of nuclei. 11 grams of nuclei will contain Avogadro number of atoms. Now we have 1 into 10 power minus 15 kg. So what I will do is I will write this as 1 into 10 to the power of minus 12 kg. Now minus 12 grams. Why? I converted this into kg. 10 power minus 3 is 1 gram. So I put this over here because I have it in grams. So I will write this here again as 1 into 10 power minus 12 grams contains how many number of atoms into it. So what is that I have to do? Unitary method. So therefore, your n value is equal to 1 into 10 to the power of minus 12 multiplied by Na divided by 11 grams. Here also I had a gram here. This gram goes away. Okay, that's the reason I put it. Okay, many of them make a mistake by doing this. Remember, whenever you are taking this, okay, the standard form, remember this mass number grams is equal to Avogadro number. That's the logic behind it. This is the formula behind it. Okay, 11 grams of the carbon level weighs Avogadro number. Sorry, contains Avogadro number of atoms. Okay, that's what we need to do. So when I do this, let us find out what is the value. So I get 1 divided by 11 will give me 0.0909. So I will write down and multiply by, oh my god, I missed a mistake over here. So I will write this as 1 into 10 power minus 12 is 10 power minus 12. 10 power minus 12 into, what's the value of Na? 6.023 into 10 to the power of minus 23 divided by 11. When I do this, what is it I get over here? I get this as, let me do the division once again. 6.023 divided by 11 is equal to 0.547. 0.547 into 10 to the power of minus 20. Hey, is it plus 23 here, right? Plus 23, sorry. Plus 23, 23 minus 11, 12 should be 11 minus 11, sorry, plus 11, or this should be 5.4 or 5.5 into 10 to the power of 10 unit. What is the unit? 10 atoms, right? This is what is required. Look at this. Calculate the initial activity of the sample in D2. We need to find out the activity. How are you going to relate the activity to this? What is activity given by? Activity is equal to lambda times N0. Okay, this is the initial activity. So I put A0 here. So lambda, see N0, what is N0? We already got this value, N0 is got here. What's the value of lambda? Lambda we need to find. What we have is lambda is equal to 0.693 divided by T. Where did you get this? We got this from N is equal to N naught e power minus lambda T. So using this expression, we have got this expression, right? So or maybe you would have read this as ln 2 divided by T. You can write like this also. Okay, now let us calculate what is this value. So this should be ln 2 is 0.693 divided by half-life. What is the half-life? Half-life is already given to you, 20.5 minutes. So remember, we have to keep this in seconds. So I'll write this as 20.5 multiplied by 1 minute is 60 seconds. 60 seconds. So therefore, now by doing this, let me find out what is this value. We have 0.693 divided by 20.5 divided by 60. 5.63 into the power minus 4. 5.63 into 10 to the power of minus 4. Now is this completed? No, it's not completed. Still we need to find the value of A naught. How do I find the value of A naught? What is it I need to do? I need to substitute this value here, right? I'll write A is equal to lambda times N0, which should now be equal to 5.63 into 10 to the power of minus 4, 10 to the power of minus 4, multiplied by, what's the value of N0? N0, 5.5 into 10 power 10. 5.5 into 10 to the power of 10. When I do this, I get 5.63 multiplied by 5.5. I get the 0.00331. I get this as 0.0031 into 10 to the power of 10 minus 4 is 6. You get so much. So let me simplify this once again. So this will be 3.1 into 10 to the power of 3 becquerels. Okay, this is how we solve this problem. I hope you have understood about this, how to solve, how to get the value of the activity, making use of half-life, and also what is binding energy, how do you use the binding energy curve to understand what is the energy release, and how do you prove that it's been released both in fission and as well as in fusion. Okay, with this we come to an end to this particular problem. We'll see the next problem in the next video. Thank you.